On our previous lesson, we have talked about three small undamped oscillations. And we have made a conclusion that in all cases, these oscillations may be described with differential equation, with ordinary linear differential equation that looks a second derivative of x with time plus omega 0 to the power of 2x, and this is equal to 0. This is equal to 0. Okay, and the question is how to solve this equation. How to solve this equation? Let's try to find the solution with function x is equal to some constant c multiplied by exponent to the power of lambda t. Exponent of lambda t, where lambda is some constant to be found, and t is time. Okay, and so let's presume that this is a solution, and how to check if it is the solution. It's necessary to substitute this in our equation. And to do this, we have to find first and second derivatives. Okay, so first derivative dx dt. First derivative will be equal to lambda c e to the power of lambda t. And the second derivative will be d2x dt to the power of 2. And this is equal to lambda to the power of 2 c e lambda t. Okay, so let's make substitution. Let's make substitution, and we'll get that this plus omega 0 to the power of 2, omega 0 to the power of 2, and this is multiplied by our function c exponent lambda t, and this is equal to 0. So such equation or such relation we have after substitution. And if this function is a solution, there should be equation, algebraic equation, lambda to the power of 2 plus omega 0 to the power of 2, and this is equal to 0. This is equal to 0. Or from here we will get that lambda to the power of 2 is equal to minus omega 0 to the power of 2. And of course, this value is negative. This value is negative, and because of negativeness of this value, we will obtain two complex roots. We will obtain two complex roots. First root is I omega 0, and the second root is minus I omega 0, where I is equal to square root of minus 1. As you can remember from calculus, or discrete mathematics, a square root of negative values doesn't exist in real numbers, but it exists in complex. It exists in complex numbers. So now it is necessary to use them. It's necessary to use complex numbers in this case. So what we obtained? We obtained that if I will clean some unnecessary things. We have obtained that if this is solution, this value lambda should be equal to this or this. So we have two possible solutions. And as we know, this differential equation is linear, and it means that every linear combination of its solutions will also be a solution of this differential equation. So it means that from here we will get that general solution will be C1 e to the power of I omega 0 t and plus C2 e to the power of I omega 0 t. Sorry, it will be negative with minus. And it is possible to prove that this is the general solution of this differential equation. Okay, so I think it is better to clean this. And also we have obtained the solution. This form of solution isn't useful. because it contains complex numbers. It contains complex numbers, and they are not useful. They are not useful in this case. They are not useful in this case. They are not convenient in this case. So it is better. It is better to find some other form of this solution that doesn't contain complex numbers, that contain only real numbers. How to do this? I think the best way is to use so-called Euler's formula. Euler's formula. It is a formula from complex analysis. Euler's formula. E to the power of e phi is equal to cosine phi plus I sinus phi. Okay, so let's use this. Let's use this formula, Euler's formula, to transform our solution. So here we have C1 sinus cosine omega 0 t plus I sinus omega 0 t. I sinus omega 0 t. Maybe it is better to write this from a new line. So I will write this here from a new line. I will write this from a new line, and the second term will be C2 multiplied by, if to take into account that cosine is an even function, and sinus is an odd function. So we'll get that we'll get here, and after the further transformation, we will get that C1 plus C2 cosine omega 0 t and plus I C1 minus C2. C1 minus C2. C1 minus C2. Sinus omega 0 t. Sinus omega 0 t. Omega 0 t. This is a result of using Euler's formula. Okay, and we may write C1 plus C2 as some value A cosine omega 0 t and minus B minus b sinus omega 0 t. And to do this, it is necessary to solve the system of equations. It is necessary to solve the system of equations. So C1 plus C2 must be equal to A, because this must be equal to this, and in similar way, this must be equal to minus b. This must be equal to minus b. Okay, let's transform the second equation in this system. Let's transform the second equation. We'll get that first equation will leave without transformation, and the second equation, if we multiple this left and right sides of the equation, multiple left and right sides by minus I, and after taking into account that I is the square root of minus 1, we will obtain that C1 minus C2 is equal to IB. Is equal to IB. So what can we do from here? It's possible to solve this system of equations. For example, we may use Cramer's rule, but it is simpler. It is simpler to just add these equations. After addition, we will get that 2C1 is equal to A plus IB, and from here we will get that C1 is equal to A plus IB divided by 2, and after subtraction, we will get that 2C2 is equal to A minus IB, and so C2 is equal to A minus IB divided by 2. Okay, do you have any questions about this? Do you have any questions? No questions. No questions. Okay, if there are no questions, so let's clean some unnecessary things. This I will leave. And I'll write just a final result. just a final result, and it means, and what does it mean? It means that we have obtained the form of solution, the form of the solution that doesn't contain complex numbers. Why? Because here we can see that it contains complex numbers I that is equal to square root of -1, and here we have two constants that are also complex numbers, but a and b are real numbers. So a and b are real numbers. So we have obtained better form of the solution, and let's use this better form of the solution. Let's use this better form, and despite of it is better form, but it is not the best. It is not the best because it can be obtained. It can be obtained more useful form. More useful form can be obtained. To do this, to obtain the more convenient form, let's multiply and divide this relation by square root of sum of squares, by this square root, a to the power of 2 plus b to the power of 2, a divided by square root of a to the power of 2 plus b to the power of 2 plus b to the power of 2, and multiplied by cosine omega 0 t, and minus b divided by square root of a to the power of 2 plus b to the power of 2 plus b to the power of 2, and multiplied by sinus omega 0 t, omega 0 t. It is looking harder than it was before, but it may be simplified. To do this, let's rewrite this in using the next explanations. I will sign this as xf, sum xf. This I will sign as cosine alpha, and this I will write as sinus alpha. I will write this as sinus alpha. So we can make a conclusion that xf is equal to this square root, and how to check if it is possible to make this substitution. How to check? It is necessary to check this relation. It is necessary to check this trigonometric relation. Sinus to the power of 2 alpha, and this is equal to a divided by a to the power of 2 plus b to the power of 2, and plus to the power of 2 plus b to the power of 2 divided by a to the power of 2 plus b to the power of 2 to the power of 2. And so from here we will obtain that it will be equal to 1. It will be equal to 1. And so this property of sinus and cosine is true for this function. So such substitution may be done in this case. Okay, so everything is correct. So cosine alpha is equal to this value, and sinus alpha is equal to this value. And from here we can write this. We can write this in a simpler way. So tangent alpha, as you know from algebra, it is equal to sinus alpha divided by cosine alpha, and it will be b divided by a. Okay, do you have any questions about this? Do you have any questions? No questions. No questions. If there are no questions, if there are no questions, we may use these signations. To write these equations in some better form. So xf multiplied by cosine alpha, cosine omega 0 t, sorry, I have some trouble with my power. We have troubles with power in Ukraine, but I think I hope I will continue. I will continue working from battery. Cosine omega 0 t minus sinus alpha sinus omega 0 t sinus omega 0 t sinus omega 0 t. And what to do with this? What to do with this? Here it is possible to remember formula from algebra. Cosine alpha plus beta. Sine alpha plus beta is equal to cosine alpha cosine beta minus sinus alpha sinus beta. Sinus alpha sinus beta. Sinus alpha and sinus beta, and it means that from here we can find that it will be xf cosine omega 0 sin omega 0 t plus alpha omega 0 t plus alpha plus alpha plus alpha. Okay, what questions do you have about this? Okay, so we have found the most useful form of the solution of differential equation of free undamped oscillations. So we have found the most useful form of the solution. Previous solutions was also true, but they are not so useful. They are not so useful as this form. They are not so useful as this form. So we'll use this. We'll use this. And this solution shows that we have harmonic oscillations. So the three small undamped oscillations are harmonic oscillations. Harmonic oscillations are oscillations that can be described with cosine or sinus functions. So let's make some conclusions. Let's make some conclusions about this solution. So as you can remember, cosine is a periodic function, and it has the period is equal to p. This period is equal to double p. This is the period of cosine. So it means that cosine of omega 0 t plus alpha is equal to cosine omega 0 t plus t0, t plus t0 plus alpha, where t0 is a period of free undamped oscillations, and the period of cosine is double p, and it means that we can write here plus 2p plus 2p plus 2p plus 2p. And what do we have? And from here we will obtain that omega 0 t plus t0 plus alpha is equal to this value. This is equal to this value. This is equal to this value. Okay, and from this equation, we can simplify it. So we can write that omega 0 t plus omega 0 multiplied by period of small undamped oscillations, and it is equal to omega 0 t plus double p And so what do we have from here? From here we may find that the period of free small undamped oscillations is equal to double p divided by omega 0 Okay, what questions do you have about this? No questions. No questions. Okay, if there are no questions, so I'll hide some unnecessary things, and we just need this result. Double p divided by omega 0. And sometimes it is possible to use so-called linear natural frequency. Linear natural frequency means number of oscillations per unit of time, and it is equal to nu 0. Okay, so from here, what do we have? So this was the differential equation. Of differential equation of small free undamped oscillation of small free undamped oscillations. Small free undamped oscillations. And this equation has the solution. This is the solution, and this value is period of small free undamped oscillations. Period of small free undamped oscillations. And what is omega zero? Omega zero is natural circular frequency. Frequency or natural angular frequency or natural angular frequency. This is the same. And nu zero is equal to omega zero divided by 2p is this is natural linear frequency. Natural linear frequency. Okay, so we have solved a differential equation of small free undamped oscillations. Okay, and to better understand this solution, let's make a graph. Let's make a picture. I'll use Cartesian coordinates. And, on horizontal axis, I'll make time, and on vertical axis means coordinate x, and the origin is 0. Okay, and how to show this function in Cartesian coordinates? It is simple. It is just cosine, and you know from math that the graph will look like this. So this is cosine, graph of cosine, and what can we say? About this? What else can we say about xf? We know that maximal value of cosine is 1, and the minimal value of cosine is -1. So if we have the maximum value of cosine, x is equal to xf. So xf 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 is equal to this. So this is xf. This is xf. Okay, and what about alpha? What about alpha? And alpha is initial phase of phase of oscillations. So alpha is alpha shows a shift of this graph. So this distance is equal to alpha divided by omega 0 divided by alpha divided by omega 0. And here we can also show a period of oscillations. The period of oscillations is equal to this distance. The period is equal to t0 to p divided by omega 0 to p divided by omega 0 divided by omega 0 divided by omega 0. Okay. What questions do you have about this? Or about free small undamped oscillations? No questions. Okay, if there are no questions, let's continue. It is necessary to say that this equation, free undamped oscillations, this equation doesn't take into account leak of energy. Leak of energy isn't taken into account. So how to take it into account? So let's have a look at the example. Let's consider an example, and I will use as example a simple oscillator, but with damping, so with leak of energy. I will remember that simple oscillator is just some fixed wall connected with spring, and this spring is connected to some mass m. Connect with some body with mass m. And here we have spring constant. Spring has spring constant key, and here we have some coefficient that shows dissipation of energy, that shows leak of energy. So I will sign this with Greek letter mu, and it means that force. Let's show axis, coordinate axis x. 0 will be here. And force that acts from spring on mass will be will be here. Because force is opposes the deformation of the spring and the velocity of deformation. So according to the definition, in simplest or according to Hooke's law, this force is equal to minus kx minus mu and dx by dt. Minus mu dx by dt. And let's use the second Newton's law. M, second derivative of coordinate, and this is equal to f. Okay, let's make substitution, and we will obtain that m multiplied by d to x dt 2, and it will be equal to, let's just copy this. It will be equal to this, and this equation may be easily transformed into more useful form. So it will look like this. So plus mu divided by m, dx dt, and plus k divided by m x, and it is equal to 0. So we have obtained a differential equation of oscillations for simple oscillator. And this equation can be written in some common form. That looks like this: d2x dt 2 plus double beta dx by dt and plus omega 0 to the power of 2x, and this is equal to 0. So first value, omega 0 to the power of 2, we already know this. This is natural angular frequency. So we know that omega 0 for simple oscillator is equal to square root of k divided by m. What about beta? Beta for simple oscillator is equal to mu mu divided by 2m, mu divided by 2m, and beta is so-called damping coefficient. It is damping coefficient. It is damping coefficient. It is damping coefficient. Okay, do you have any questions about this? No questions. Okay, so I will leave just a final common form of this differential equation. We need just this. And as we obtain. So this is differential equation. Differential equation of small free damped oscillations. And this equation is closer to real situation. Because it takes into account leak of energy or energy dissipation. It takes into account leak of energy. And what else can we say about this? That beta is damping coefficient. Beta is damping coefficient. Damping coefficient. It is necessary to say that sometimes in internet and in books you can see that the damping coefficient is equal to this value, beta divided by omega 0. So sometimes you can see that damping coefficient is this. But it is not so important. It is not so important to make a difference between them. So we can use this or just beta. For this situation. So let's try to let's leave just this. Okay, what can we say about this equation? As you can see, the equation of undamped oscillations than was before, and this equation they look very similar. But for second equation we have additional term. And I think if we will get rid of this term, we will be able to use this solution for this equation. So let's try to get rid of this term. To do this, I'll try to make a substitution. The x is equal to gamma y. X is equal to gamma y. And to make this substitution, it is necessary to find first and second derivatives. First and second derivatives. So first derivative is equal to dx and dt, and this will be gamma dy dt plus d gamma and dt y. Okay, and the second derivative will be equal to d dt, open brackets. In brackets we have first derivative. In brackets we have first derivative, and here we will obtain that it is equal to this derivative, open bracket, and this expression will be here. This expression will be here. This expression will be here. Okay, so let's open the brackets. Let's open the brackets. It will be equal to gamma second derivative of y and dt2 plus d gamma dt and dy and dt, and plus this again, because I'm calculating derivative of this term, and plus second derivative d2 gamma dt2 and multiplied by y. Okay, and we have obtained that it is equal to this plus 2 multiplied by this and plus this. And plus this. Okay, do you have any questions? Do you have any questions about calculation of second derivative? No questions. No questions. Okay, that's fine. That's fine. And that's fine. And I will leave just this second derivative. Okay, let's make a substitution. Let's make substitution in our differential equation. differential equation of three small undamped oscillations. So after substitution, we will obtain this plus 2 beta open brackets and here will be in brackets, here will be this sum and plus omega 0 to the power of 2 gamma y, and it is equal to 0. And it is equal to 0. It's necessary to say that just now it doesn't look simple, but we will simplify it. And so to do this, let's transform this. So let's divide this by gamma. Let's divide this by gamma, and let's group similar terms. So we'll have second derivative y by time, second derivative, and plus 2 Here we have just 1 divided by gamma d gamma dt and plus beta d gamma dt plus beta. And of course here we have dy by dt, and plus here we have just what we will get. We will get 1 divided by gamma, and this plus this plus 2 beta divided by gamma, 2 beta divided by gamma, and 2 beta divided by gamma, and d gamma dt, and plus omega 0 to the power of 2. Omega 0 to the power of 2. Y is equal to 0. And this is equal to 0. Okay. What questions do you have about this? Okay, so let's try to find such gamma function that makes this bracket equal to 0. Let's find gamma function that makes this bracket equal to 0. So it is necessary to solve this equation. So this must be equal to 0. This must be equal to 0. Okay, the variables may be separated in this differential equation, so we will obtain d gamma divided by gamma, and it will be minus beta t. And after separation, this differential equation may be integrated. It may be integrated. So we can write this. We can write this. And of course, it is necessary to add constant of integration. But we need to find any gamma function that is a solution of this differential equation. Any gamma function. So let's choose the simplest form. The simplest form will be with constant of integration that is equal to 0. It will be the simplest form. So from here, after integration, we'll get natural logarithm absolute value of gamma, and this is equal to minus beta t. And of course, from here we have that absolute value of gamma is equal to exponent of minus beta t. And from here we have that gamma may be equal plus or minus exponent minus beta t. And both signs, plus and minus, may be used. Both signs may be used, but and we may choose any of them. So let's choose plus. Let's choose plus. So gamma is equal to exponent of minus beta t. Exponent of minus beta t. And I will remember that this gamma is a solution of this equation, a partial solution of this equation, and this equation derives from this condition that this term is equal to 0. And after taking into account this condition, we will obtain that simplified differential equation. So I can clean some unnecessary things that we don't need anymore. And and let's find let's left only some necessary things. So we have obtained simplified equation, and gamma is known, is already known, but it's just necessary to find y. Just necessary to find y, and I think we will do this. We will do this on our next week. On our next week. So after substitution, we have obtained this equation. And it doesn't contain first derivative of y. It doesn't contain first derivative of y. Okay, what questions do you have about this? Okay, so if there are no questions, so thank you for your attention. Thank you for your attention, and I hope to meet you tomorrow. I hope to meet you tomorrow on practice. Okay, have a nice day.